No, it's like, no, I know, but it's like.
So I started writing down some equations so we could go a little faster. But the first thing I wanted to just point out is, so next Monday, we're not going to meet. We had a discussion about this way back. And we figured that the best thing to do, the last section we have is just on chapter 13. We're going to talk about statistics. And that's going to be the remainder of our class time, except for the last day that we were going to do a final exam review. And so it would have been difficult to do that all, whatever. We'll not meet on Monday, and then we will meet on Wednesday when we'll start talking about statistics. So we're going to wrap up chapter 12 today, which, as I pointed out, doesn't have an additional homework. It's the same homework as for the previous PDEs chapter. Today I'm going to try and make that linkage clear is the only thing I want to do. As we go back, and I think that's probably the right way to think about chapter 12 in the context of the final exam too, is that I may use these equations to motivate the kinds of problems we'll pick, but the PDE solution techniques will be the ones that we learned by looking at the PDEs themselves, the heat equation and the wave equation, basically, if that makes sense. So these equations, the continuum mechanics equations, motivate our study of PDEs, essentially, is the right way to think about it. So these guys, the conservation of mass equation written in two different forms, the conservation of tracer equation written in two different forms, and then I'm just writing the momentum equation in one form, but we could have also written out an advective form as well, are the things that we use to kind of motivate the style of equations we're interested in. So that's the way to take our approach to chapter 12 in mind, is whatever the PDE's questions will be for the final will be kind of motivated by these equations. But I don't expect you to know how to solve these equations in general because they're nonlinear and horrible. So we will always be simplifying them back to something that is more tractable before we work on it. Does that make sense? So the reason why we have this chapter at all is just to motivate why we work so hard to get here and think about PDEs and all the tools we needed to get there. Statistics, we will use computers a little bit in the statistics class, not so much. I have a few codes written in MATLAB, which I'm happy to share with you, which make things easier. You could use Excel if you wanted to, if you don't know how to use MATLAB. We're just going to do things like take averages over and over again and talk about what that means for the homework problems. But we'll make that homework will be due like way toward the end of the semester. So we'll have a lot of time to talk about that when we get to statistics. I just wanted to give you a heads up that there will be some computational bits, which will be a little different. But it's not a lot of programming. It's just sort of, like I said before, it's boring to do statistics with like things you can do by hand. You actually just want to do like the average 1,000 times rather than 2 or 3 times, which is what at least I have the stomach for by hand. Okay. All right. So, right. All right. So that's that. All right. So, continuum mechanics. So you guys started out talking with Majid, and from what I understand, he walks through at least the derivation of the mass equation and the first part of the momentum equation, although he didn't talk much about this side of the equation. Is that roughly right? Okay. So what does this equation tell you? Yeah.
When you change your mass, the volume is compensated by the maximum.
Exactly. So this is sometimes called the flux form of this equation. And so this is the rate of change of density, so mass per unit volume. So in this one, it's good to think about a little box. And inside the box, there's some stuff. It's got density, and if I integrate over the whole volume of the box, I get the total mass. And so this thing is telling you about the rate of change of density inside the box based on the divergence of rho times v But what do we know about the divergence of rho times v integrated over a volume? The divergence of anything integrated over a volume. Why does it look like that? Because that is this. Right? We have our divergence theorem. So this term is telling us that in order to keep track of the stuff inside the box, you just need to see all the rho times v coming and going from the outside, in and out of each side. So that's the way to visualize and think about what that equation means. Is this a linear or a nonlinear equation? It depends on whether rho varies or not, I guess, is one way to think about it. So we're thinking rho is varying because there's a ddt, but there's this funny product. So we have a nonlinear part. So if the velocity field is being solved for from this equation, and the density is being solved for by, say, this equation, then we have a nonlinear product. But you could also say, well, actually, I've just got rho v together, and I've got rho v together over here, so maybe rho v is just an object. Rho v is the momentum per unit volume, and I'm not thinking of it as a product. That's a cool thing to do. People have thought about that for a long time, but then there is a nonlinear term here, because if rho v is one product, here's another v multiplying by it over here. So we can't get away from the nonlinearity, however we pass the buck between those two equations. We can simplify it by looking at certain limits, or taking something that's fixed, like the density is constant everywhere, then that makes this equation linear. It's just a constraint on the velocity. Okay? So this equation is nonlinear, that equation is nonlinear, this equation is nonlinear. But under certain circumstances, which is what I want to get to today, we can linearize it by thinking about simplifying the statement of the problem, or thinking about particular limits where maybe some of the terms are smaller than others. Okay? So what's this equation? Yeah.
It's the same one as above the gradient though.
It's the same as above if I distribute this derivative. Cool. That's one way of thinking of it. But I could also think of it just directly here. So this object, these two terms together, is sometimes called the material derivative. And did Majid talk about how you get this from integration by the chain rule? He walked through this. So essentially, if I think of rho as something that depends on space and time, and then I try to take its total derivative, rho, then I have one part that depends on time, and I have one part that depends on space, so I need the derivative of space with respect to time times the derivative like that, right? Does that make sense to everybody? So then there'd be another one for, oh, sorry. dy by dt time, d rho by dy. So that's because I'm thinking of rho as being a function not only directly of time, but of x, which also depends on time, or y, which also depends on time. Okay. But what is the rate of change of x with respect to time in this conception? So it's density of a part of a piece of a fluid or a solid, and that piece of fluid or solid is moving around. So density at this point was earlier located here. So what I mean by dx dt and dy dt is the rate at which that hunk of stuff is moving. Its displacement in x per unit time, or its velocity. So that becomes the velocity dotted into the gradient of rho, and d rho by dt. That's this operator. And I like to use a big DDT on this because the big DDT reminds us that the rate of change is actually the velocity of the thing, like the fluid or the solid or the gas. In this form, I could have used any old dx dt I liked. It could have been, if it was a wave-like propagation, this would have been the speed of the wave, not the velocity of the fluid. Okay, so some people will tell you that the total derivative is the same as the material derivative. They're a little different because the material derivative means I'm taking the total derivative and then I'm also thinking that the displacements in space are related to the motion of that material. So it's sort of an extra little piece of information. Okay? Yeah.
When would displacements in space not be related to motion?
So this is what I'm saying. So if I shoot light through something and that light is changing the density as it goes, then this would be the speed of light, not the advection of the stuff. So there are other processes which propagate through space that might affect your variable that would travel at a different speed than this together. The material derivative is the special one, which says we're following the motion of material parcels in solid or liquid or gas, and when they're displaced, we call that rate of displacement the velocity of that underlying fluid, or solid, or whatever, underlying continuum. That makes sense to everybody? Okay. All right. So, and did you guys talk about the tracer equation? No. Okay. So, what if there's something that's marking those parcels? Temperature, energy, salinity, moisture, water vapor content. I could think of the rho times some concentration of that stuff as being something else I might want to move from place to place. Does that make sense to everybody?
I think we might have actually talked about this. We
We
did,
use C.
yeah.
Did you use a theta?
Yeah.
We use C.
C, yes. So C is the same game. So theta, jumping ahead quite a few steps, it is what I use as the symbol for potential temperature. So potential temperature is a marker of the thermodynamic properties. It kind of behaves like a concentration. It's, I guess technically in a gas, it's a concentration of entropy, but that's more sophisticated than we need to know. This equation is something that's like the first or second law of thermodynamics written with a potential temperature in it. So I do that in the notes. I kind of show you how you convert from one to the other. But basically, the key point here is, so how many unknowns are in this equation? It's density, and there are 3 components of velocity. So we have 4 unknowns, but we have only one equation. So we need some more equations if we're going to try and solve it. So I say, well, let's consider the momentum equation. It's got density, so that's still only 4 unknowns. 3 components of velocity, still only 4 unknowns. That's still true here, still true here. This guy, the stress tensor, we're going to talk about in a second. But how many equations is this? I have 3 different components of velocity, so I have this equation repeated 3 different times. Right? So I do have 4 equations. This guy plus this guy and the 4 unknowns, rho, and the 3 components of velocity. So that would be awesome if I knew this object, the stress tensor. So I'd be able to solve everything. But in fact, we find in the real world, the stress tensor depends on other things like the pressure, which we're going to talk about in a second. What that means is that if I say the stress tensor is the pressure, so if I say sigma equals minus the pressure times the identity tensor. Plug that in, then I get minus P there, gradient of the pressure, then that would be awesome, except now I have 5 unknowns and 4 equations. So I need an additional constraint to give me both the information about pressure, and density, and velocity. So what's something that relates the pressure to the density? Like what kind of an equation is that? We actually talked about it once. Right? Remember we had the ideal gas law? So this is a thermodynamic relationship, and it says, okay, if I know the pressure and I know the volume, oh, sorry, I'm not blind. If I know the pressure and I know the density and I know the temperature, now I have another equation. Awesome. So I can add this one in, and now I've got 5 unknowns: pressure, density, 3 components of velocity. 1, 2, 3, 4, 5 equations, but now I've got temperature too. Yeah.
In the momentum equation in the top line, what's this V and then the symbol?
This little hat, yeah. It's the tensor product of these two guys. So remember when we wrote v dot v for a vector dot into a vector, we can make that a scalar. But if you think about it in matrix form, like this, that's how we did it, right? We had 1v here and 1v here, and this is like, you know, n by 1, and this is 1 by n. And so we put those together and we get a single scalar as the answer. We could have also multiplied it the other way and done a column times a row. And this would have been 1 by n, and this would have been n by 1. Wait, we got that right? Yes. And that's not a scalar, that's actually a matrix. That's n by n. So if I take my 3 components of the velocity and dot it into itself, then I would get a scalar that's close to the kinetic energy. But if I do it the other way, and I say, give me the x component of the velocity together with the x component. So vx, vx, vx times vx. Now vy, vx times vy, vx times vz, vy times vx, vy times vy, y times vz, 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 y, vz, vx. So there's 9 of these covariances in this object. And then I take the divergence of it, which means that I'm now going to take the ddx of this row and the ddy of this row and the ddz of this row, and I end up with a vector left over. So this is like really playing harder games with our relationship between the divergence and a vector and also our matrix pieces. Okay? So this is the product of the velocity times the velocity. So that part's pretty straightforward, but it's the product, not collapsing them down like a dot product. It's the outer product where you take every component times every other component and make a matrix out of it. So I put that little wedge there to indicate that. Okay? So, but we'll explain what it means in a second. Yeah.
Can you explain briefly what a tensor is? I don't know.
A tensor is like a vector, but bigger. Is the simplest thing. The easiest example to think of a tensor is in fact this one, which is just the product of 2 vectors, but just keeping all the components rather than that part. And the reason why we call it a tensor, so one thing of the things that I would like to do in revising the notes is to introduce tensors alongside vectors way back when we were talking about that. it's most closely related to that concept of like, a vector is a vector because when you rotate the coordinate system, it transforms in a particular way. And a scalar is something that doesn't change when you transform the coordinate system. A vector is a thing that transforms like a product of two vectors. A tensor is like the thing that is what happens when you write two vectors times each other, component by component.
So is this like double-sided arrow above the sigma is like the tensor?
Yeah, so this guy is also an object. This guy is also an object that has this same shape. So when I take its divergence, I get a vector out of it. I'm taking the divergence of it, and the answer to the divergence is a vector. So it's like this, except this one I don't know anything about what all the 9 elements are, except I know it's got 9 elements. Okay? So or in this particular case, it has, this is the identity matrix of 9 elements, and then I'm just multiplying by a scalar pressure. So when I take the divergence of this guy, I just get the gradient of the pressure. Okay, so this is a little messing around in both our matrices and our tensor or calculus, vector calculus pieces to keep things together. All of that stuff that we learned is important even in just figuring out what it means to write down this equation. Does that make sense to everybody a little?
What is that called again, the tensor thing?
This is the stress tensor. Yeah. Okay. So I guess the whole point here was we needed some kind of thermodynamic information to close our system. And in order to get the thermodynamic information, now we needed a temperature equation to start talking about thermodynamics. So in fact, you can't even do the kind of the compressible gas problem without thinking about thermodynamics. You don't have enough equations to close the system. We have this one that tells us it's about mass, this one that tells us about momentum, but then we need a pressure to talk about the momentum, and in order to get a pressure, we have to talk about the thermodynamics, which means we need to talk about the temperature too. So it's a big mess of equations to think about. Yeah?
So this is just for gases, right? Because we're using fluids. What if it were for like rocks or something?
Perfect.
If you row GH.
Excellent question. If I took it for a liquid, so what's the difference between a liquid and a gas?
Gases expand.
Gases expand and compress a lot. In fact, liquids compress and expand a little bit, but not so much that it wouldn't be a bad approximation to say that the density was constant. So if the density is constant, what happens to this equation? Or this equation may be easier. What's the partial derivative with respect to time of a constant? 0. What's the gradient of a constant? What's a constant times something else? If it's not 0, I could divide through, then that whole equation becomes just this. And what about the momentum equation? If this rho is a constant, I can pull it out, right? If this rho is a constant, I can pull it out. If this thing, we will get back to it, if this rho is a constant, then I can divide through by on the whole equation. And so then my equation becomes something that looks like this. So I still don't know what my stress tensor now per unit density is, but everybody else is just written in terms of velocity. So hey, look, I've got an equation. I've got one equation on 3 components of velocity. I've got 3 more equations on 3 components of velocity. If my stress tensor over density is simple, like just a pressure, then I actually have enough equations to solve without all that thermodynamic stuff. So the incompressible case, where you're not converting between heat and volume, essentially, you don't need all that thermodynamic stuff. So that's a great question. That's exactly the kind of simplification that this leads us to think about. Does that make sense to everybody? A little? I mean, this is the kind of manipulation we have all the tools to think about pulling constants and scalars inside and out of these complicated derivative operators now. While I don't expect everybody to kind of track all of the pieces of that story, the manipulation tools are just the same ones we've been talking about all along. So now if you go and take a fluid dynamics class, they're going to say, let's consider the incompressible fluid, and then they will get to this equation, and then they will get this form of this equation, and then you are ready to proceed. So while we can't cover all the fluid dynamics and all the solid mechanics and all the gas dynamics that we might like to think about all those things in this class, you can at least see that you've got the tools in place to start manipulating these complicated equations. Does that make sense? Okay. But I wanted to say one more thing about this heat equation before. So this isn't quite the heat equation we studied last week in the PDEs. What's different about it? Right, do we have this term in our heat equation from last week? Yeah. Do we have this term? Yeah. Well, we got this new term now. So what does this term describe? The velocity dotted into the gradient of the temperature, and it came from that thing I just erased right here, which was the displacement of material parcels. So this term, which is called the advection term, is about what happens to the temperature if you displace particles that are labeled with their temperature. So if I take some air from over here with one temperature and I bring it over here, that's this term that would describe both the disappearance of it there and the reappearance of it here. So, does that make sense to everybody? So why did this term not appear in all the examples, like the heating of the bar that we have in the homework, the heating of the plate?
Because we were dealing with solids.
We were considering things that were motionless, yes. So essentially we were just not letting it move around. We were just balancing this term versus this term. Perfect. So that's exactly the piece. Now, could we use something fancy? Like, remember when we talked about scale analysis and dimensional analysis to figure out how big the different terms in this equation were? This one has like a temperature scale divided by a time scale. This one has a velocity scale times a temperature scale divided by a length scale. And this one has a diffusivity scale, whatever that is, times the temperature scale divided by a length scale squared. They all have the same temperature scale, so I can cancel that out. When is this term going to be bigger than that term? Or how do I compare this size of this term to the size of that term? Sorry, my L's are very fun. This is an L. Sorry, does everybody remember this stuff? If I left too far to the past. We talked about, in dimensional analysis, we talked about guessing how big this term was by saying, suppose this is the rate of change of temperature per unit time. So if you tell me how big the temperature variations tend to be, give that a name, capital theta, and how big the time that I'm paying attention to, give that a name, capital T. This term is about as big as that ratio. And this term is about as big as the velocity, however big the velocities tend to be, times the temperature, however big those variations tend to be, divided by the length scale of variation of the temperature. So that's what how the gradient works. And then this one is the diffusivity times the temperature scale over the length scale squared, because this is a second derivative. Does that make sense to everybody? So how big is this term versus that term? If I divide this term by that term, what do I get? I get V divided by L times T. So how big is that ratio? compares, B is the scale of what? Yeah, and L is the scale of what? It's the scale of the gradient. So when does the gradient, if I had a rise over run, or a size of a hill in temperature, this thing would have the scale, whatever the size of that scale of variability was. If I had a big hump of temperature, the width of that hump would be really proportional to the magnitude of this gradient, or the inverse width would be proportional. Does that make sense? So that's the thing here. And then T is the time scale that we're considering the rate of change over. So this ratio says if my velocity is fast enough to cross that length in that amount of time, oh, except I've gotten, thank you. Cross that length in that amount of time, then what would happen? Which term would be big? My velocity is big, crossing that distance in that amount of time. How big is this term versus this term? Maybe think of the different limits. The velocity is really, really big. How big is this term? Big. Big compared to what? Big compared to how long it takes to cross the distance that's sort of the typical distance in this variation versus the typical time in this variation. We make this term big compared to this term. Does that make sense to everybody a little? We could go this way too. Let's compare this side to this side. That one goes like velocity, we do the other way around. Diffusivity divided by length squared. Length squared, one of the lengths cancels and the velocity comes down here. So diffusivity compared to the length times the velocity. When is this term going to be really big compared to this term?
Okay, sorry, just to reiterate, you're getting those by dividing
This scale factor for this term by this scale factor for this term. Alternatively, I could have said this is the scale factor that goes together with kappa L squared theta over V dot grad. I'm basically examining how big this term is versus this term. And this is the scale factor that comes out. And notice that both this scale factor and this scale factor are dimensionless. So we talked about dimensionless numbers being sort of more powerful than dimensional ones because however you could zoom in and zoom out and get the same answer. So when I'm looking at the ratio between terms, I'm kind of taking advantage of that zooming in and zooming out insensitivity. Yeah.
I forgot what case. Is that diffusivity?
This is diffusivity of heat
Okay.
in this equation. Because we just talked about the diffusivity of heat. In the heat equation, diffusion balances the rate of change. Now we have this new term, trying to understand it. So when is the diffusion going to be a lot bigger, making this term bigger than this term? What do I need to do to L's and V's and K's? Make the diffusion really big, or make the velocities really small. And then the total limit, the one that Ali correctly identified before, if the velocity goes to 0, if it's a solid, there's no motion, then this guy goes to infinity. But so the heat equation applies as a good approximation to this when the motions are small compared to the diffusivity. But in order to make that comparison have the right units, because we can't compare meters per second to a meters per second squared, a meter squared per second, we needed to multiply by some typical length scale. Does that make sense to everybody? So under that this condition, we get the linear heat equation out of this approximate form of the much more complicated tracer advection diffusion equation. Okay? So our heat equation we studied last time is hiding inside of this way more complicated nonlinear differential equation. So what's the other linear PDE that you guys talked about within the G? And the heat equation and the wave equation. So the wave equation is a little harder to get to. It's hiding inside of this one together with this one under some specific assumptions about the stress tensor. Okay. There is also a momentum diffusion equation hiding underneath this one, which looks like the heat equation, but for every component of momentum. If I put in a viscous stress tensor, I could make momentum diffuse viscously through, just like heat could diffuse diffusively. All right, sorry, that was poorly stated in English. But I could make this term really big and make it viscous, and then I would get an equation, but didn't worry about gravity, didn't worry about this advection term, that what looked like an awful lot like a heat equation, because we can guess kind of what that's got to look like, divergence of a gradient of something. So let's write it out. So sigma over rho naught was approximately a viscosity times the gradient of velocity. Then this term would become divergence of the gradient, the constant viscosity, V. And if this term was big compared to this term and this term, we would get dV by dt equals V Laplacian heat. That's sort of approximate. So how does this equation compare to our heat equation? It's similar, but there's one important difference.
Sorry, is that a 2 under the V?
Yes.
In the equation above?
This is sorry.
Okay.
I'm saying it's constant. I just
Okay.
don't want you to worry about taking derivatives of the viscosity. Sorry.
The viscosity variable.
Yes, this is viscosity. This is viscosity is the thing that's like diffusivity but for momentum. So you could have written with this with a K if you wanted. This is just something that has the units of meters squared per second, and it's the rate at which momentum spreads through something that's kind of gelatinous or gooey.
So when you're saying that, so are you saying the divergence of sigma over rho naught equals that entire thing, or is it just sigma?
Sigma over rho naught equals this object,
Okay.
which is, sigma is a tensor. So this is a funny object. This is a gradient of a velocity, but not a divergence. So this is one of the, just like the velocity times velocity gave us a matrix, this is a divergent. This is like the same thing, but with dx, dy, dz acting on vx, vy, vz, but keep all the combinations together in a 3x3 matrix. Then when we take the divergence of it, we end up with this equation. So it collapses into a Laplacian of this. So, and realize we're jumping through a lot of things that are outside of what we've done, but aside from the steps in the derivation from here to here, how does this equation compare to the heat equation? What do you see that's different now? Yeah. This is a vector heat equation. So each component of the velocity is diffusing like temperature was diffusing. Temperature is a scalar. So this is a whole other beast, even though in some sense it's the same thing, just take the X component, and then the Y component, and then the Z component. Each of them is viscously diffusing through this viscous material like a heat equation. So you could solve this equation with the separation of variables like we talked about on Monday for velocities, but you have to do it 3 times over. You have to hit each component of the velocity and have boundary conditions on each component of the velocity. Fourier transform this side, blah, 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 on the same way we did it where we talked through doing it on Monday. Does that make a little sense? So we can get a heat equation from one particular assumption about this stress tensor. Yeah.
So what is the reasoning for not having an advective term on this?
Because the same reasoning as this. That this is called the Peclet number. And if I say that that's the inverse, 1 over the Peclet number. So if the Peclet number is very, very small, it means that diffusion is very, very large. The Reynolds number is U is the velocity scale times the length scale over the viscosity. And if this is very, very small, then this advection term is dominated by this viscous term. So things like the mantle have very, very small Reynolds numbers. And so you can neglect the advection term altogether in the momentum equation and just balance the stresses with applied forces versus the acceleration. And frequently they actually neglect the acceleration too. And they just talk about the forces and the stress tensor in being in balance, in a static balance. Okay? We still haven't gotten to our wave equation. So, let's go back a little bit. In the wave equation, or one particular, there are actually, I know at least 5 different wave equations that you can derive from this set together with that. We're going to talk about sound waves, which are maybe the cleanest to derive. Okay? So, if we can't actually use the constant density equation because sound waves are actually compression of density. So we need to go back up one to this guy. Or write that one too. So and now that we've erased the density part, we actually have to go back and think a little bit about thermodynamics. And in sound waves, there's one particular kind of thermodynamics that's important, which is one of the Maxwell relations. Entropy constant. Entropy constant. Sound speed. Okay, so this is a bit of thermodynamics. We definitely don't have time to talk about too much. But basically the rate of change of pressure, if you hold the entropy fixed, is proportional to the, one of these should be density. Which one is this one? The rate of change of density. So if I'm compressing, I can balance the pressure versus the change in density. Okay? And there's a proportionality between those two rates of change. And in fact, the constant of proportionality is the sound speed, which is really the derivative of density with respect to pressure holding the entropy fixed, is the definition of the sound speed. So this is a hunk of thermodynamics we don't need to know very much, but it allows us to rewrite this equation because we can handle that kind of guy, and this equation because we can handle that kind of guy. So doing that, we got from this equation over here, erase it a little. We got the rate of change of pressure with respect to time is equal to minus the density times c squared, the divergence. Switching use for V's, which one am I using? V's. So this is just this equation with this little piece of thermodynamics added. Everybody see that? How do I get an equation for the divergence? I have one over there. Can I take the divergence of this equation? I guess I could. It's a bit nasty. But I could take the divergence of this equation and at least one part of it would hit a divergence on this guy. And one part of it would be some nasty, horrible thing here, which we would then neglect because one is nonlinear and two, it would be hard to think about. We could worry about it, but we wouldn't. One part of it would be the divergence of the gradient of the divergence of the stress tensor. So now it's kind of a double divergence on this guy. And then one would be this, which we could balance off apart that. But to make a very long story short, we can write this like this. And you find that there's an equation that works like this. It says that the pressure variations look like a wave equation with the speed of sound as the velocity of propagation, as the speed of propagation. So I do this in somewhat more detail in the notes to go through the intervening steps. But the point I wanted to make here is that hiding inside of these equations and combinations of these equations are also wave equations. This one is for sound. There's one for love waves and Rayleigh waves and ocean waves and Rossby waves that are part of El Nino and internal waves that are the agent that the way that the density vibrates in the ocean that we talked about with that bouncing ball of density. All of those things are sitting inside these equations. So we have only really three forms of equations to think about, but like all of the tools we've been using this whole semester are needed to talk about different ways that these equations behave. That's really the essence of why I wanted to build up to continuum mechanics, is just to show that like everything we've been doing has an application in this set of equations. These are sufficiently complicated, but that's the case. So we can write these equations down, and if we were like some sort of omniscient being, we could just see what that meant. We would know if we saw these equations written down what fluids would do, what solids would do, what liquids would do. But in our much lower form of appreciation of this, we have to approximate these equations, throw away terms, think about different balances, get to linearization, use Taylor series, use Fourier series, use all those tools to get us down and boil these equations down to a form that we can manage so that we can understand how they behave under different circumstances. Alternatively to the approach we've taken in here, you could have taken these equations and started coding them up in a numerical model. And we could have spent the whole time talking about different ways to stick these equations into a model and solve them, which would have ended up touching on a lot of the different points of these same pieces that we've been talking about. If you take Chris Huber's class on modeling, GEOL0350 instead of 350, that's essentially the approach. You take these same equations, but you code them up into numerical algorithms. They help produce solutions of them. And you think about how the different numerical algorithms work. And hiding underneath those are the same concepts of like Fourier series, Taylor series, discrete versus continuous, discrete approximations to integrals, all the things we've done, but just from a different perspective. So these two classes are intended to give you the opportunity to think about these same sets of equations from both perspectives.